Okay, let's do some easy energy practice. We've got a box of mass M is released from rest at point A, the top of a long frictionless slide. Point A is at a height h above the level of points B and C. Although the slide is frictionless, the horizontal is not. The coefficient of kinetic friction is mu, and the horizontal distance x, just like it has labeled there. Nice. So find the speed of the box, and the box is at h over 2, so it's halfway here. Well, this is just going to be a conservation of energy compilation. So remember, for A, I'm going to start over on the side here. We have mgh is equal to 1/2 mv squared. The m's cancel out. Boom, gone. Now, h is equal to 1/2 of big H there, so we're going to have 1/2 g big H is equal to 1/2 v squared. Cancel out the halves for funsies, and square root, so v is equal to square root of gh. That's it for A. Easy. Okay, so now let's look at part B. Find the speed of the box when it reaches point B. Well, it's the same kind of thing. We just have 1/2 in with there. So let's do it over here, I guess. So we have mgh is equal to 1/2 mv squared. Cancel out the m's just like before. So we have g big H is equal to 1/2 v squared. Solving it for v squared, we're going to get 2gh square root is equal to v. Ta-da! So that's for B. Now let's look at C. Determine the value of mu k. So that box comes to rest at point C. All right. So we're still doing conservation of energy, but we're going to be comparing some other stuff here. So let's compare potential energy. So we're going to have mg is equal to, what happens in this area? It's work. So we're going to have work because it's going to equal the work done. Whenever you have a change in energy, it's from work. So you have energy when you start off, you have no energy at the end here. The difference is work, just like in real life. Okay, so we have mgh equals w. What's w going to equal? W is equal to force times distance. Just placing it, whatever. All right, but what's the force? The force is a force of friction. Force of friction is equal to mu times your normal force. What's your normal force? Your normal force is mg. So it's going to be mu mgd is equal to mgh. M's cancel out just like before. G's cancel out just like before. Well, not just like before, but you know. So we're solving for mu k. Oh, that's okay. So h over d is equal to mu k. And that's that. Easy. Let's look at part D. Now assume part B and C were not on the same horizontal level. In particular, assume that the surface from B to C has an uniform uphill slant, so that point C we're still on a horizontal surface of x from B, but now at a vertical height above B. All right, so what's happening is it's doing this. That's what's going on now. So there's a uniform upward slope so that point C is at the same horizontal distance, but it's up. All right, and it's still going to have friction. So we're going to answer the same question here. We're going to do it the same kind of way. So we're going to start off with energy. So we're going to have mgh. This is what we're starting out with. Now this is going to equal our work just like before, but this time we're going to have some potential energy. All right, so plus mgh. This mgh is talking about this height here. All right, we'll calculate that in a little bit. All right, so we're just looking for mu again. All right. So for work, we're going to plug in. We're going to solve for W just like before. MGH is going to be the same. Now, it's going to break apart into the friction force times distance, just like before. Now for the friction force, we're going to break that apart. We're going to get mu times force normal. What's the force normal going to be? The force normal is going to be mg times the cosine of theta. All right, that's equal there because your normal force is going this way now, just cancel out this way, right? So you gotta keep track of your normal force, and then times d. What's the distance here? Well, the distance is going to be the hypotenuse, right? The hypotenuse is not x anymore, but we do have a triangle. This is x, that's a theta. So it's going to be x divided by the cosine of theta. So in a way, it's kind of the same. And it makes sense that it's the same because it's a dot product. So you guess you could have gotten away with it, but that's bad habits, you know. All right, plus. There we go. Plus, there's a height here. There's an m. There's a g. What's this guy gonna be? This guy is going to be a tangent. So it's going to be, because it's opposite over adjacent, right? So x tan theta. Boom. Got it. All right, what can we cancel out here? M's are gone. G's are gone. Nice. Oh, this is all right. So all we gotta do is solve for mu. So let's finish here, and we're going to subtract x tan theta, and that's going to equal mu x. And then we're going to divide everything by x, right? That's it. So mu is going to equal h minus x tan theta over x. Boom, boom. There it goes. Oh, hold on. If the slide were not frictionless, determine the work done by the friction. Oh, the slide on the left. Oh, okay, all right. I got it now. I got it. If the slide were not frictionless, determine the work done by the friction as the box moved from point A to point B. The speed of the box as it reached point B were half the speed as we calculated in part B. Okay, that's not so bad. So part B is dark blue. So this velocity here is half once it gets to B. So what's the work done to make that half? All right. So here's what we have. We have our starting energy. It's going to be another conservation energy. MGH. That's what we started with. That's going to equal 1/2 mv squared, which is the movement, plus W, because that's the work done, right? That's only on this part. We only care about going up to point B there. Now, we know some stuff here. Do we need to know the... we just need to determine the work, so we don't have to break it down at all. Okay, so we're going to have an M, we're going to have a G, we're going to have a big H. That's going to equal 1/2 times M. Now the velocity is going to be this guy, halved. So we're going to put a square root of 2gh over 2, parentheses, and then in for the velocity. All right. Now it's just a solving game. So now we got to solve for W. All right. So we can do a little simplifying here. We can cancel out the square root and the square, but this guy will change to a 4 in the denominator, right? So let's rewrite what we have. we've got mgh is equal to, let's combine the half and the quarter. So 1/8 m, oh, there's going to be a 2 that pops up, gh plus w. All right. Okay. So the 2, let's do a little reducing here. That reduces to a 4. Nice, nice, nice. So we have mgh, and then you have a quarter of mgh. All right. So 1 mgh minus a quarter of mgh is going to equal 3/4 mgh. 3/4 mgh. And that's it. So the work is going to be 3/4 of the energy. And that makes sense because the velocity is squared. So if you half the velocity, you quarter the energy. Where'd the other 3/4 go? They went to work. Yeah, we could have done it easier. Ah, well, it's fun to do algebra, isn't it? I'm sure you're missing out on it. All right, let's do another one. A student uses a digital camera to record the following data about a ball as it slides down a curved, frictionless track. All right, it's curved and frictionless, so acceleration is not going to be constant. The initial point is 1.5 meters above the ground, and the ball is released from rest. Prints up the following data and tries to analyze it. Well, I hope he does a good job. Based on the data, what is the corresponding heights for each data point? Okay, so let's kind of visualize this here. He's got a track doing something like that. All right, so your potential energy is changing to kinetic energy. So what we're going to have is we're going to have mgh is going to equal 1/2 mv squared. So we have the velocities here. So what we want to do is figure out the heights. Let's figure out a formula for it, and then we can figure out what the heights are. So we're going to solve for h. Cancel out the m's. So h is equal to v squared over 2g. All right, that's good. But that's only half of the story here. So this is calculated how much it drops. This would be h here. To figure out the height, we want to know what's the other side of the vertical distance. Now, since the whole thing is 1.5 meters, so that means this column here, we'll call it height, above the ground. To figure out this guy, we're going to do 1.5 minus the formula we just got here. So v squared over 2g. All right. Now, if I were you, because I did do it, I would just type it into the calculator, use the lists function, and then you can do it all at once. So 1.5, 1.4, 1.2, 0.8, 0.8, and that's a good sign because those are the same speed. That should be the same height. 0.9 slows down. It should be going up. 1, 1.1, 0.9, 0.6, and 0.5. And there we go. So those are the heights for each point there. What time segment experienced the greatest acceleration? What is the value of the acceleration? All right, so when we're talking about B, we're talking about acceleration. What's the formula for acceleration? It's the change in velocity divided by the change in time. So which one has the biggest change in velocity? Easy, because they all have the same delta t. So which one has the biggest delta v? It is going to be this first section there. So you just got to figure out the slope, basically. So we're going to have 1.41 minus 0 is equal to 0.05 minus 0. And you're going to get 28 meters per second squared. Nice. How about that gravity? How would this value change? How would the values change if the ball were replaced by an identical ball with double the mass? Well, in case you forgot, we canceled mass out a while back, so they would have the same values. That's good. That's all they want. All right. Hopefully you're okay with that. Ask any questions if you want. It'll be hard to time travel to this point. Okay, let's keep going. A car with mass of 800 is traveling with an initial speed of 10. When the brakes of the car are applied, the car starts to skid and experiences a frictional force of mu k equals 0.2. What is the skidding distance of the car? Well, the skidding distance of the car is going to be calculated. Let's figure out the acceleration first. So acceleration, what is slowing the car down? It is the friction. So acceleration, remember, is equal to force divided by mass. So we're going to have a force of friction divided by mass. So force of friction is going to be mu mg divided by m. Hey, look at that. Masses cancel out. All right, so it's just going to be equal to mu g. I'm just going to plug it all in here. And then we got to use our famous equation. V squared is equal to V0 squared plus 2AD. We're ending at rest. We're starting at 10 times 2 times the acceleration. The acceleration is mu times g. Mu was 0.2 times g, which is, well, 9.8, times d. We're solving for d. Maybe the signs bother you. Your acceleration is negative because you're accelerating the opposite direction as you're moving. Either way, so doing some solving here, your distance is going to equal 25.5 meters. Easy. Okay, let's look at part B. How would the skidding distance change if the initial speed of the car were doubled? Hey, all right. Hey, if we double the initial speed, well, I mean, you could always just grind out the numbers, but when you double something that's squared, this guy here is going to be quadrupled, right? The value, because we, distribute the square. So you are, for part B, you are going to have 4 times the distance. Ta-da! 20 squared is 400. 400 divided by all this nonsense. So that's 0.1. Yeah, it's going to be the same. It's going to be that. Anywho's. All right, moving on for part C, number last. How would the skidding distance change if the initial mass of the car were doubled? Well, boy howdy. If you doubled the mass, you double the amount that was canceled out. So there would be the same distance. Nice. And that is it. Too easy, right? Hopefully. Hopefully you had as much fun as I did. All right, like and subscribe and ring the bell for more videos coming soon.